Yeah, we are recording now. This is meeting number 13 of the scicloj-ai group. We're learning about closure and AI, and today we're lucky to have Nathan Marz, who will talk about Agent-o-rama. We have both Nathan and Hugo of the Rama team. And yeah, we are 9 people at the moment, and let us begin.
Okay, sounds good. So yeah, let's keep it open-ended. So again, just jump in with questions whenever you like. I'll be showing a lot of code, so I'm sure you'll have lots of questions. So let me share my screen. Okay. Um, okay, so first of all, Agent-o-rama, what is essentially two things, and these things work hand in hand. First, it's a library for building um, agents as graphs of closure functions. You can also use, it also has a pure Java API as well. And as a tool for orchestrating agents, it has like a lot of really nice properties. Parallel execution of agents is extremely easy. It's ultra scalable, fault tolerant, and it has built-in deployment and storage. By storage, I mean like the storage you can use is like as good as a database, but you don't have to deploy it and manage it separately. And the second piece is it's an evaluation and observability platform for your agents to, first of all, before you deploy them, actually be able to measure how good they are, and then after they're deployed, be able to monitor how good are they doing on real production examples. And these things are linked because, of course, the way that you define your agents is going to affect the way that you can test them. And so these are not independent things. They're not completely independent. So actually, let me actually just start off by showing an agent. So here I have actually a whole bunch of agents, which I'll be using to demonstrate Agent-o-rama. But right here is a research agent. Think of this as like OpenAI Deep Research. It's like a really bad version of OpenAI Deep Research. But it's a really good demonstration of how Agent-o-rama works and what it can do. So why don't you guys give me a topic to have it research about?
Pine trees.
Pine trees. Let's see. How about uh, the role of pine trees in, let's say, Lisp history, let's say. Okay, we'll see what it comes up with. Um, okay, so here we can see it jumped from the agent view to the agent trace view. So we're actually seeing a live trace of the agent running. And so right now it's doing an LLM call to start the research process. And the first thing it does is it creates a bunch of analysts who are going to analyze this topic. And basically every analyst is a persona, which is going to be used to prompt the LLM to cause it to generate different responses. Um, I think it was the first time I ever ran it that it was not working. Huh. Well, that's unfortunate. It always happens during a live demo. It's possible that the OpenAI API is down. Oh, you know what? I think the OpenAI API was just slow. Okay, so that actually just took a while, but it did finish. Okay, and so the first step is that it asks for feedback. So this is what the LLM generated. So these four personas, just different people with different backgrounds. So we'll just use this. We'll say no, and then we'll actually let it finish. And then here you can actually see it running. And you can actually see, like for example, here, well, that already finished. But you can actually, if you click on the nodes, you can actually see like a live stream of what the LLM is generating for that node. And you can see by this trace, whenever you see a branch, it's running those things in parallel. And that's very, very easy to define. We'll get into later what the green and orange nodes mean, but that has to do with like fan out and aggregation. So we'll let this just run in the background, and we'll come back to it later to look at the trace and see everything that's going on here. As you can see, we have a lot of numbers here, like analytics, and if you actually click on nodes and you scroll down, You can see lots of information about what happened on the node as well as what happened in the agent as a whole. Okay, but we'll come back to that. Okay. Okay, so first thing I will say is just how important evaluation and observability is for building agents. And we were talking about this a little bit before we started the recording. But like testing is super important for software in general, of course. And just the only thing with LM-driven applications is that LMs are so non-deterministic and so unpredictable. Unless you're taking a very rigorous approach to how you're testing your applications, you're not going to know where you are in terms of how good it is. Like ad hoc testing is not even close to good enough. If you're only relying on ad hoc testing, just doing a few different prompts, it's going to be super biased and it's going to perform very badly in production, where the kind of prompts, the kind of data you're seeing is going to be very, very varied and different. And there's all sorts of reasons why an application you have deployed and haven't touched will regress. One could just be that the LLM itself changed. Like if you're relying on the OpenAI API or the Anthropic API, like it could start producing different results, which are not performing as well as what it used to for one reason or another. Another thing that can happen, which has nothing to do with LLMs, it's very common for agents to have a retrieval step where you're searching databases or searching vector stores, and then you get all the information, you throw it in the context window, and that becomes part of the prompt. Well, as you're adding data to retrieval stores, it's possible that the quality of the results goes down just because it's sifting through more stuff, or the way the search works isn't that great, and that can cause it to regress again without changing your application. So it's not just about testing beforehand; it's about continuously testing while it's in production to actually understand how it's performing. And in terms of like testing space, like it's a pretty intimidating testing space. Like you're for most of the applications, you're just dealing with natural language input, so you're testing against the entirety of human language, and so you have to be rigorous and data driven about it. And so what Agent-o-rama does is provide the tools for being able to approach this in a data driven way and making that as easy as possible. So at the center of this is data sets, just collecting data sets of examples. And every data set example, these are just screenshots from the Agent-o-rama UI, by the way. But every example has an input and a reference output. Here they're just strings, but they can also be data structures. So here we have the inputs and map, and there is no reference output. But the idea behind the reference output is that's like a golden truth. So this would be like a data set for classifications. And so given these inputs, that's how they should classify. And you can use the reference outputs during testing. Like the most simple way, run my agent or this section of the agent against that input, see how it categorized it, and just compare against the reference output to know if it was correct or not. That's the easiest way to do it. Other times you can use the reference output to be more like guidelines. It's very common to actually use LLMs for evaluation. So the reference output could say, like the answer should contain this information, perhaps in this order, and it should not contain this information. And then the LLM can compare the output of the agent with the guidelines from the reference output to actually score how good it was. So these are the ways you'd use a reference output during testing. Okay, and that brings us to testing, actually running what are called experiments. The beauty of an experiment is that you take a data set, and then you take a target, which could, again, be a whole agent, or it could be part of an agent, and then you run that target against all the examples of that data set, and then you evaluate the results using any number of evaluators. And then we'll get more into evaluators later, but the idea behind evaluator is it scores it. Evaluators can be an LM evaluator, as I mentioned, but they can also just be regular code. It could be like, does it match a regex? Is the length of the response under a certain number of characters? And whatever you could imagine, it could just be regular code. And here, summary evaluator would mean like a statistical thing like false positive rate or F1 score or something like that, where you're not looking at individual examples, but looking at the data set as a whole. This is a screenshot of what experiment results would look like. So here you can see that on the detailed results, you can see for every example, what was the input, what was the stats on the run in terms of token usage and latency. You can see what was the reference output from the data set, and then what was the actual output from the agent run, right? So here you can see it's it was correct for the first two. You can see they matched, and you can see the evaluation. This only has one evaluator. It matched true for those first three examples. And then at the top, you can see just overall summary stats in terms of what was the average latency, what was the token count, and so on. And when it comes to experiments, like it's not just about quality. It's about the trade-off between quality, token usage, and latency. Token usage is essentially cost, how much money you're spending for the response. And if you can cut the latency by 75%, and then your response quality goes down by 10%, maybe that's worth it. That's for you to decide as the builder of the application. And so experiments let you actually see the results across all these different dimensions, so you can decide for yourself what you want. But you use experiments for many things. You use it during development to test new versions of your agent. You can just test the same agent, but with different parameters, like a different model version. Maybe part of your agent is like the number of iterations it should be doing searches, and maybe that's a parameter you want to test against it. And then another very important thing you use experiments for is back testing, right? So, try your hardest to build your agent and come up with good examples that you think your users are going to do. And then when you put it into production, you're going to be surprised by how users are using your app. And then it may not perform well for those, but you can take those production examples and backtest against those for your next version of your agent and actually see, okay, am I actually doing well on the examples of production, which I wasn't doing well on before? Okay, so that's like the offline testing portion, and so then we come to observability, actually seeing what's going on, and so the core of observability is tracing, and so again with agents where you have so much uncertainty, so much non-determinism, when something goes off the rails, you need to be able to figure out why it went off the rails, and so with tracing, you need very deep and detailed information about what happened at every step, what model calls happened, when they happened, where they happened, what database calls were there, what were the inputs and outputs to the database calls, and so on and so on. And so that's what Agent-o-rama provides. This is just free out of the box. And we'll see a lot more of this through this talk. Then there's human feedback. So this is something we're actually just about to release. We're probably going to release it like on Monday or Tuesday. But this I think is a very important part of the workflow. At the end of the day, you cannot only rely on LLMs for evaluating the performance of your LLM-driven applications. That's like, it's very easy to get into circular logic with that, which just doesn't make sense. Like you need humans actually stepping in to actually evaluate how things are doing. And so what we've added is just a full feedback system that just integrates with all this and makes it easy. So like here would be an example like on a trace of adding a feedback to the root of the agent. Right, so you would score it. You could give it scores. Like here, it's giving it a helpfulness score and a conciseness score, and then you could leave a comment, and then other people would be able to see that. And you could also leave feedback for individual nodes as well. And then there's these human feedback queues. So the idea is that you could automatically, let's say, take a sample of runs from production and add them to queues. And then so that humans can look at the queues and then just evaluate them, and then those will go to their respective traces, and then you'll have telemetry on them. Here we have two examples. Like production eval would be like, let's do like a 1% or 10% sample of all runs, have a human actually look at them like a subject matter expert and actually say how good they were. And then maybe you take all runs that aired, put it in the errors data set, and have a human look at those as well. And this would be like what a queue looks like, where you could then see all the stuff that's waiting for feedback. And then when you click on an item, you'd be able to actually, this is a form to actually fill out the metrics that you should be evaluating on, leave a comment, and then move on to the next item. Okay, and then the last piece of this is about tying the loop between observability and evaluation. And this would be automations. And so there's a whole bunch of different automations we have built in. You can also build your own automations. But the two most important ones are first, automatically adding like production runs to data sets. So you might have, for example, like a slow runs data set, and you want all runs over 60 seconds to be added to the slow runs data set. And that'll just automatically accumulate, and then you can look at that later and just see every single production run that took a long time. You have full tracers for them. You can dive in and see what went wrong, and then you can later test against that data set as you improve your agent so that it's not so slow on those examples anymore. Maybe all runs with errors go to an errors data set. Maybe a sample of runs go to the production sample data set. You just have a lot of flexibility in how you form these data sets, which we'll see. The second really important action is online evaluation. And so you want, again, you want to be able to actually have metrics over how it's performing. Um, and so for example, you might run an LLM to actually evaluate how helpful was this answer, or how relevant was this answer, or how grounded was it in the retrieved documents. You do it on a percentage of runs because it may be too expensive to run on all runs, and then you get automatic telemetry on that. But then you can use these actions for other things like triggering PagerDuty webhooks for failed runs and so on. And this is like completely pluggable as well, and very easy to set up. This is what the form looks like to add an action. You basically just name the rule. You say what it applies to, whether a particular agent or a node within the agent. You say when should it start applying, so you can actually backfill. You select an action, you give parameters to the action, and that's it. You say add rule, and then it will start running. And then at the bottom, you have filters. So you can actually put filters for which run should it actually apply to. Maybe it's all runs. Maybe it's only runs where the input matches the regex, or it's only runs with a latency over a certain amount, and so on. And then you have the last piece of observability is telemetry. So actually seeing like aggregate time series graphs over how it's performing. And so there's a lot of telemetry built in to Agent-o-rama that you just get for free. And so like here we're seeing like how many times was the agent invoked over time? What was success rate over time? What was latency over time? Total model calls over time across all agents, across all nodes. How many model calls per agent run? What's the latency of the individual model calls? Store read and store write latency. These are Rama's built-in stores. So how fast are reads and writes? And what's the distribution of those? Time to first token. This is a very important one. So this is basically a measure of how responsive your app is. And so that's like essentially the amount of time before the user would see any feedback from your agent. So that's a very important one. Then you have total token usage and so on and so on. And then here would be for any online evaluation actions you set up, you'd have a graph set up just automatically that would just show you what the score is over time. Okay. You guys have any questions on that before I move into actually building agents? Okay, let's move on to the code. We'll be looking at the UI a lot. Okay, sorry, just making sure I'm still connected because I'm just talking in silence here. Okay. Okay, so as I said in the beginning, Agent-o-rama is two things. It's a library for building agents, right? And then the evaluation observability platform. So let's now look at actually building agents. So Agent-o-rama is heavily inspired by these two tools from the Python ecosystem, LangGraph and LangSmith. Agent-o-rama is much closer in execution to LangSmith and LangGraph. It takes from LangGraph the idea of specifying agents as graphs of functions, but the way it actually implements that is very different. And LangSmith, Agent-o-rama largely has all the features of LangSmith. There's still some, I guess, more minor features LangSmith has that Agent-o-rama doesn't have, but they're mostly equivalent at this point. And these are like the differences between LangGraph and Agent-o-rama in terms of execution. I just put it here for completeness, but we don't have to dive into it. Okay, so let's get into the code. So Agent-o-rama agents are very simple to define. It's a very like small API. They're just graphs of Java or Clojure functions, and we'll of course be looking at the Clojure API today. In terms of like how you deploy them, they deploy to a Rama cluster. So Rama is a platform that we built that does both computation and storage. It's basically like a self-contained platform. We're not going to talk that much about Rama today. It's a super deep topic, but basically like it's free to use up to 2 nodes. You can download from a website and it just runs as a cluster. And it's a like super scalable platform. And it has like operations are built into Rama. So deployment, updating, and scaling your applications are all one-line CLI commands. That's all just built in. It's all like very robust and fault tolerant. And then the other thing, because you're running this on your own clusters, like any data within your agents would stay within your own infrastructure, right? Like we're not running anything for everybody. And this is very different than a lot of the tooling in this area, especially evaluation. Observability is like cloud platforms where you're sending like very sensitive data in your traces to third-party providers, but that would not be how you'd be running it here. Okay, so here's the code example. So this is like the hello world of agents. And so this basically define something called a module, and this is what you deploy to the cluster. And a module defines any number of agents as well as any amount of other things such as storage. Like you might be defining these stores, which we'll see soon. And those would be deployed as part of your model. They're not deployed separately. But here we're not deploying, we're not doing any stores. We're just making one agent. And this is just plain Clojure code here. So we're saying new agent called hello. We'll add a node to the agent called say hello. So the name of the node is say hello. The next one is what are the nodes that this node can output to? This is just a single node agent. So we set that to nil because there are no other nodes. And then we have the actual node function, which is a plain Clojure function. That first argument that's called agent node, that's how you interact with the agent graph, mostly just to emit to other nodes or to provide a result to the agent. And so here this takes in one argument username, and all it does is it sets as a result of the agent, hello, username, exclamation point. That's it. This would be how you would run it in your REPL. And so you would say you'd create something called IPC, which means in process cluster. And this just simulates a full Rama cluster in process. So here we just launch our module with a certain amount of parallelism. And now we're good to go. So we create something called an agent manager, which lets us actually access agents within that module. We get a client to that particular agent within that module. Again, remember, we named the agent hello. And then we can invoke it. You just call agent invoke on the agent with Alice, that returns hello Alice, right? So you can treat it, it's just like calling a function, but it's actually going to be running remotely on a cluster. Okay, so let's look at a more interesting agent. So this is a looping agent. So this has multiple nodes, and it also has a loop inside the agent. And so you can see we have 3 nodes. We can see the start node, and you can see the start node says it emits to node 1. And you can see in the body, all it does is emit to node 1. And all this is doing is it's accumulating a list while it decrements a counter. So it's going to go cycle through until the counter gets to 0, and it's going to essentially just accumulate those numbers in a list. You can see in node 1, that can emit to start or end. And you can see in the body, if the counter is 0, it emits to end. If the counter is not 0, it emits back to start with something added to the list, right? And then the end node is just going to just put the result for the agent. So let's actually look at the UI for this. Okay, so here you can see this is just a graph of, this is literally what we coded, right? Our start node, node 1, and end, and what they're allowed to emit to, right? Start can only emit to node 1, node 1 could emit to start or end, and end does not emit to anyone. Here I have like a trace, and if I actually look at a trace, here I'm actually seeing a node in the trace for every time a node was invoked, right? So this was called with the argument 3, and you can see node 1 is called 3 times, and start is called 3 times, because that's it, just you see it just going around the cycle. And then you can see the final result was 2, 1. And then if we actually look at the trace, we can actually see at the start, the input was like an empty list and 3, and you can see it emits to node 1, the empty list and 2. If we click on this, we then go to the next node. Right now we're on node 1, right? And we can see this got, the empty list and 2, and then it emits, this is actually a nested list right here, a list containing 2 and 2, and we can just keep going, and we can just see how it's doing, right? We see timings for every node, when it started and finished, and so on. There's no LLM calls here, there's no database calls, so there's not that much going on, but you can see, you can kind of see here the value of splitting it into nodes, right? What defining an agent like this does is it gives you a granularity for tracing, and you'll see later it also gives you a granularity for streaming, and it also gives you a very easy parallelization mechanism. But from a tracing standpoint, we just automatically capture inputs and outputs every node. You're able to see that in the trace, and that's super valuable for debugging. Okay, so here's an example of actually using an LLM, right? This is the reason that you'd be even thinking about using Agent-o-rama in the first place. And so the way you'd interact with an LLM or any shared resource would be using this abstraction called agent objects. And so the first thing we do, we declare an agent object for the OpenAI API key. And so this is just getting it from my local machine when I deploy it, right? It's just in an environment variable. And then you create an agent object builder, and this is actually going to create like an actual LM client on the actual cluster when it actually wants to talk to the LLM, right? And you can see that when it constructs the OpenAI chat model, it's getting the OpenAI API key from that setup argument. And then it's parameterizing it and building it. This is using a library called LangChain4j, which is a Java library. It basically provides like a common interface for all chat models, which is very convenient. You don't have to use LangChain4j with Agent-o-rama, but it is convenient. We do integrate with it, but you can just as easily use your own libraries yourself. And then if we actually look at this agent, again, this is a single node agent, and you can see in the body of the node, the first thing it does is it says get agent object for OpenAI, and that'll get an instance of that chat model. And then it just invokes it, right? It creates like a few messages to pass to the model for chat. And then it calls lc4j/chat, and that will block until it gets a response. And then this is just send the response back to the as a result of the agent. So this is not really doing very much, right? It's just doing a single chat invocation. Now there are yeah, there's one thing to note here, which is very important. Um, like that chat call right there, that's a blocking call, right? And it's an LLM call, so that can take 10 seconds. And so normally it would be dangerous to block for a thread for 10 seconds. It would be like super resource inefficient. But Agent-o-rama it runs nodes on virtual threads. So it's actually perfectly fine to block like that. If you're not familiar with virtual threads, basically the way virtual threads work in the JVM, it's an awesome feature that was added in Java 21. But when you do a blocking call, the virtual thread actually unmounts from the platform thread, and it's not using any resources anymore. So you can have like thousands or millions of virtual threads that are blocking, and it's still using the underlying resources efficiently. This is it's much more convenient to write code like this than with like an async API with callback hell. And so this is like really nice and makes really nice code like this. Um, cool. Let's actually look at a trace of the chat agent. Okay, so here I asked it, what is the fifth tallest mountain? Again, we only had one node. If we look at the node, you can see that um, it automatically captured the call to the OpenAI model, right? So we have this operations section, and this captures all nested operations, which will be model calls, database calls, vector store calls, and so on. And so here we can see the input, right, was these two messages, and we can see stats in the input. What was the input token count, output token count, total token count, what was the response, what model was used, why did it finish, at what time did it get the first token back from streaming. So you have all the information you need here to see what's going on. And then the rest of the trace is the same. Okay, here's an example of using built-in storage. So as I was saying, the built-in storage that you can use in Agent-o-rama, which comes from Rama, it's very high performance, durable storage. It's just as good as the database, but it's built in. You don't have to deploy and manage it and configure and optimize and scale it separately. It's just built in. It deploys with your module, and it exists within the same processes as your agent. Here's just one line to declare. So at the top, we say declare key value store. We say the keys are strings and the values are longs, and we name the store counters. Stores always begin with $2. And then you can see in the body of the node, you just say get store, and now you have a client to that store, and then you can just do blocking operations on it. In this case, it's a key value store, so you can do gets and puts on it. So that's all this is doing. It's just getting a value for that counter name and then incrementing it and putting it back in the store. So just super, super convenient to use. And this is really, really useful for any sort of state that you want to keep for your application. Now let's look at a trace again. Right, so here we have managed counter, and then you can see, right, the nested operations. We see the store read that it did. We see the store write that it does. We see the latencies, the parameters, the results. So again, very, very, very detailed traces. Okay, so that's actually most of programming Agent-o-rama. That's like as I was saying, it's a very simple API, but there are a few more bits to it that are important and relevant. So let's go through those as well. And so something that comes up is that you may want to for one reason or another, you may want to split your agent into multiple agents and actually have the agents coordinate with each other. And so that's extremely easy to do with Agent-o-rama. It's called subagents. And so here we actually have two agents defined. So the first one's called helper. It just does some math on the input. And we have another one called main. And you can see the way in the body, it gets from the agent node a client for the helper agent, and then it just invokes it. The same way you'd invoke it, like I was showing in the beginning in like the test code when using in-process cluster. It's the exact same API. And so this just composes just like function calls, and it just works like that. And let me actually show an example of this. Right, so here we have a trace, right? So we can see in this node, as a nested operation, we can see it did an agent call, and we can see what it did with that agent. What it called it with, what it got back, and so on. You can also see stats about the subagent call. And so something I didn't show yet, but you can see we have this telemetry here on the right, which is showing telemetry about this particular execution of this agent. And this telemetry actually splits the stats by agent. So we can actually see that what time was spent in the main agent versus what time was spent in the subagent calls, right? So even if it's recursive or looping or whatever, you would see this broken down by agent and see how many times those were invoked and how many times their individual nodes were invoked and so on. There's only one node for each, right? So we see the stats for those. So again, like super useful to see what's going on and why. Okay. All right. So tools. So a really common thing with LLMs is that you want them to be able to like perform actions. And to do that with something called tools, where we actually tell the LLM, hey, you have these tools available to you. Here's the names of these tools. Here's their parameters. Here's a description of what the parameters are. And you can invoke those. If you invoke those, you send me a message, and then I'll send you back the result for the tool. And so this is an example of defining tools with Agent-o-rama, right? So at the top, we have a tool. This is for just doing exponentiation. Everything's communicating with strings, of course, because LMs just talk in strings. And so you see the arguments are just going to be a map of arguments. Here we would have the base and the exponent, and then we would just do the math and then return it as a string back to the agent. And then here you can see for down below, this is how we describe the tool to the agent. This is all just a wrapper around the LangChain4j API for defining tools. But basically you just say what's the name of the tool, what's the description of the tool, and then you give it a JSON schema for what are all the parameters, and then what are the types of the parameters, and what's the description of the parameters. You want to give as much information here as possible so that the LM doesn't hallucinate and get confused, right? So it does the right thing. That's why this is so verbose here for how it describes the tool. But one of the things the JSON schema does is that it means that in your argument map, they will be parsed to those types, right? So like you can see like when we get the argument for base, we get a number back because when we told the LM, we told it like we told the schema for this is a number, right? Not like a string or whatever it wants to do. Here would be a number tool for doing division, right? Very similar, but different arguments and different descriptions, right? And then you just define your tools as a vector of tools, and then this is going to be used in a couple spots to actually invoke the agent with it. But like here's a chat agent with tools, right? So the beginning is the same. We're just defining our OpenAI API agent. And then you can see we have a line there where we define the tools agent. And so this is just a built-in agent in Rama where you give it a vector of tools, and then it will be a subagent that can execute those tools for you. And tools can do anything. They can be simple functions like I showed. They can also talk to databases. They can do themselves LLM calls. Like it can be whatever you want, right? It's just arbitrary functions. And those tools have access to like agent objects, so they can, or stores that you defined, or whatever you need. But here we have a chat with tools, and so this is basically like the React agent. That's like one of like the common like agent examples you'll see. But this basically just does a chat, and you can see in the chat request, it provides the tools, right? So that will configure the chat to the LLM call, so it knows what tools it has available. And then it looks at the AI message response, And if there's any tool execution request in an AI message, then we invoke the tool agent with those tool calls. That will give us back the results of the tool. We add those results to our list of messages, and then we're going to recurse, right? We're going to emit back to our own node, right, with our new list of messages, which now includes the tool, not the tool calls by the AI, as well as the tool results. And now the LM for the next invoke will have the full history of the chat, and it'll be able to either provide a response or maybe it'll do another tool call, right? And so if the tool calls are empty, that means it had a result, and then that's what we provide as a result of the agent. Let me show like a trace of this. Okay, but here, so let's look at this trace, right? Here we can see I asked it, what is the exact value of this complicated math expression, right? So this is something an LLM cannot do. It cannot do exact math like this. Like it needs tool calls to be able to do this. Otherwise, it's just going to guess, and it's going to guess, it'll be like 20% off or something like that. But to give an exact answer, it needs tool calls. And we see in this trace, we have 3 executions, right? Because it has to do two tool calls, right? One to do the division, one to do the exponentiation. But we can see here on the first node, we ask what's the exact value of this, and then we can see that it did a tool call. The agent did the LM did a tool call, right? It's asking for a divide between those numbers that were in the prompt. And then you can see this is where it this is where it provided the this is where am I? Okay, yeah, okay, sorry. This is the tool call by the model. Here's what we call the tools agent, right? And this is what came from the model, right? And then the result of the tool agent is going to be the result of the division, right? We go back to the next node, right? And we see that the input of this node, we can see the whole conversation, right? The AI did a tool call with those arguments. This was the result from the tool agent, right? This number right here, right? And then we can see that the model is doing another tool call. It's asking for tool execution, and it's asking for what we can see here. It's asking for exponentiation, right? And then we can see here from the last one, now we do OpenAI call. Now the finish reason is stop. That means it actually has a final result because now it has all the information it needs and because it did all the math with tools. And then we end up with the final result, which is yeah. So yeah, it's just 3.146 times 10 to the 10th. Okay. Okay, a few more things with tools. So with all this stuff, like you always have to consider that LLMs can hallucinate and stuff can go wrong. They even with the tight JSON schema, they might still hallucinate, and models vary on how robust they're going to be about calling tools. And so part of the tool sub-agent is actually handling errors. And so by default, the way it handles errors is that if there's an exception, it just turns that exception to a string, and then it tells, as the result of the tool call, it's going to say, you had an error, here was the exception. And then the agent and then the LM can use that to perhaps do another tool call where it fixes the mistake that it did. But you can also customize how it handles errors. Maybe you want a static message, maybe you want a different message depending on the type of the error, so on. Another thing about the tools agent is that if the LLM did multiple tool requests, the tools agent will actually execute those in parallel automatically. And so if your tool calls themselves can be expensive, that's actually important and can really improve the latency of your agent. Maybe it's doing a bunch of expensive database calls, for example. And so having those run in parallel is like really, really helpful. And then finally, I was saying that your tool functions can do things like talk to database or LMs or do other agent calls and so on. And you do that when defining the tool by saying include context, and then you get access to the agent node from which you can get your agent objects or agent clients and so on. So then the body of the tool call is just like the body of an agent node where you have full access to everything within the agent. And those run on virtual threads as well, so you can block. Okay, so aggregation. So this is another big piece of how Agent-o-rama works, which is very important, which lets you do like fan out and fan in patterns. And I was alluding to this when I was showing the research in the beginning. But here we have an agent that's doing some fan out followed by some aggregation. So here we create an agent called ag. You can see the start node is actually going to emit to node one many times, right? And it emits like that many numbers. So I call it with five, it's going to emit five times in node one with the numbers 0 through 4, right? And you can see node one takes in that number as input and it just emits to ag that number multiplied by 10, right? And you can see ag node, right, is defined as an ag node, and then it has this extra parameter called vec-ag. And what that means is it takes all the values that were emitted to it, and it's going to use that aggregator to put them into a single value. In this case, vector means just aggregate them into a vector. So we're going to end up with the numbers 0, 1, 2, 3, and 4 in a vector. But they might not be in that order because this is running in parallel, as you're going to see. And then this just sets as a result the ag val, which is just going to be the vector of results. So let me actually show a trace of this, because this is pretty illustrative as to what's going on. Okay, so here we can see, like we called it with input 5, and the final result was 0, 10, 30, 40, 20, right? And so we emitted 0, 1, 2, 3, 4, but they actually ended up in the result out of order. Again, because, and you can just see here how things are running in parallel, right? So we had our start node, right? It emitted 5 times. So you see node 1 5 times. And because it's branching like this, that's how you can see that they're running in parallel. And then, these, and by parallel, like again, like Rama, Agent-o-rama, this is a scalable system. So this could be running not just on a different thread, but on a completely different node across the cluster. Like you don't really have to think about that. But then you can see they all emit to ag, and you can see this receives as input all these inputs, and it just produces the vector of as output, and that's the output of the agent, right? And they just get aggregated in the order in which they come in, depending again on the parallelism, the way they race with each other to produce a result. But you can see the ag node waits for all of the expected input to come in before it finishes and actually runs its own node function. So that's how aggregation works. Yeah, okay. And so basically the ag start node, it starts the aggregation scope, and then the aggregation node actually does the aggregation for anything that happened in that aggregation scope. And this can be nested. So you can have aggregation scopes within aggregation scopes, as I'll show in a second. Okay, so this is, for example, from the research agent, where we do have nested aggregation. As you can see, questions is the first aggregation scope, and then generate question is another aggregation scope. And every green node has a corresponding ag node, which is an orange node, right? So that's an aggregation scope. These are all aggregation scopes. And then this whole thing is an aggregation scope as well. And then you can see at the bottom of this, it's beginning another aggregation, where it's doing more stuff in parallel. Cool. And so what aggregation does is it'll just automatically execute the subgraph in parallel. Any amount of nesting is allowed, and you can also have looping within your ag subgraphs, which is actually something that's happening in the research agent. Okay, another important piece to this is human in the loop. And so again, like LM-driven applications are um, uncertain. And you might run into a situation in your agent where it's so uncertain, you don't really want to proceed without a human looking at this. And so this is just a built-in feature to Agent-o-rama. It's really cool how this turned out with the API. It's really neat. But it's literally just an API call where you say get human input. It's just that call there, and it just blocks the node. It blocks the whole agent until a human goes in there and answers that. This is just the code from the research agent, right? So you saw this in the beginning, right? It said, do you have any feedback on the set of analysts? I answer yes or no. And then if you were to, that human yes call is itself getting human feedback. And then it will get more human feedback for what is the feedback, which will then be fed back to the LLM to generate a new set of analysts. And so you just block, right? That's the prompt you'd see in the UI, or if you're using the API via the API. And the feedback is just the string that the human provided, and the agent can keep on using that. So I think it's pretty neat how that turned out. This is what it looked like in the UI, where you can just see it on the node, and then you can provide your response right there. But you can also do this via the client, the API as well, which would be a more likely way if you wanted to integrate it into your app and actually have a user provide feedback. Is what the API looks like for human in the loop. And so, we saw agent manager, agent client at the beginning. That's just how you connect to a cluster and get a client to your agent. Here, it's actually invoking the agent using agent initiate. And what that does is it just starts the agent, right? But that'll run in the background. And then the return value from that is called the agent invoke. And you can use that to get a result, or to just get information about like what's going on with it. In this case, we say agent next step. And so that just blocks until there's something until either it's done or there's human input is needed. Those are the two possible things that can be the next step, right? And so here we say, if the step is a human input request, then we will prompt at the console for human input, and then recur with the next step. Otherwise, we're done, and that's going to be the result of the step, right? So this is the basic driver you can use to um, communicate with your agents from your web server or something like that. Yeah, and there's also this function pending human inputs where it's possible that you have 10 nodes in parallel asking for human input. This will actually just return all of them, everything that's pending right now at this moment. Okay, that's basically everything for building agents. So I just want to show the full client API, which again is not that long, but there's some new stuff here. The first one would be that's how I showed before how you make IPC in process cluster, which is used for like development or experimentation. This is how you connect to an actual Rama cluster, which gets you a cluster manager, which is exactly the same, works exactly the same as IPC. Then from that cluster manager, we can get an agent manager for a particular module. From the agent manager, we can get clients. And then initiate is just as I described before, how you initiate an agent. Right? You call agent result to block until it has a final result. You call agent next step to get block until there's either human input or result, as I just showed in the last slide. There's just a predicate to tell you if the agent invoke is complete or not, pending human inputs I described before. Agent invoke is just a combination of initiate and result. So it just blocks until it just invokes it with those arguments and blocks until there's a result. And then we have some streaming methods. Uh, Agent-o-rama streams at the granularity of a node. And so on this first one, we're streaming for the first time. The first time that node is invoked, that's going to be the stream of what are called chunks from that node. Usually chunks would be tokens. Like a string would be like it would be like a string of tokens. And so the way streaming works in Agent-o-rama, when you're using like LangChain4j, that's one of the nice integrations. It'll automatically stream stuff from the model back to the node, and then you can get it from your client like this. And so then the callback function tells you what are all the chunks we received so far, what are the new chunks for this callback, and then reset. The reset boolean there just means that there was an error and the node had to retry, and so it ended up restreaming from the start. And then complete means it finished. There's no the node finished. There's no tokens left. And then agent stream all is to stream every time that node is invoked, right? So if there's like a loop in your agent where it's going to invoke that node many times, here you're actually going to see every time um, any of those invoke streams, and you can see the argument's a little bit different here because it's actually broken down per invoke, what the tokens are. Okay, so let's look a little bit more at the research agent that we ran before. Okay, so the role of pine trees in Lisp history. Cool. Okay, so this is the result it produced. And so you can see here, it's like nicely structured, right? We have an introduction, we have a body, and then we have a conclusion, right? And then we have sources. And actually, if we look at, I'm actually really curious what it actually came up with. But like these links work. Interesting. Interesting that it linked for this topic. But these all work, right? So this, that's not always true when you call an LLM. A lot of times it gives you hallucinated links, but the way this research agent is structured, these will be valid links. And so basically, just to review again what it's doing. So first it generates these personas, where in this case, our personas were, Dr. Lisa Evergreen, a botanical historian from the University of Pine Studies, Professor Robert Codewood, who's a computer scientist, blah, blah, blah. So the idea is that if you think about how these people will respond to things, they're going to come from different perspectives, they'll prioritize different things. And so these personas will be used. We're just using the same LLM all the time. The LLM doesn't change. What's changing is how we're prompting it. And when you tell it to respond from the perspective of these personas, it really does change what the LM, how the LM responds and what it focuses on. And that's especially relevant for here because it's doing this retrieval step where it's actually fetching information from the internet. And so those personas are going to want to research different things. And so that's going to determine what is going to go into the context window when we actually generate a report at the end. But we generate personas and we go into this questions loop. And you can see all this node is doing is it's initiating the question loop for every single persona, right? We have 4 personas. And so we have 4 branches of this, all which are running in parallel. And so if we look like down here, we can see like this conversation that happened. We had this interview loop where we have the LLM is asking questions to the persona, and it's generating first it generates a search query based on that persona. It's fetching information, and then it's asking the persona to respond using the context of that information that was fetched from the internet. In this case, it's doing a general internet search and also doing a Wikipedia specific search. And then this is answering with the context and also providing its sources. Again, these sources came from this retrieval steps we did before. And then he asked another question, which will go into the next iteration. It's only looping 2 times, but you can configure this to loop as many times as you want. But you can see it generates first when we generated the question. Um, um, then based on the persona, the LM is going to end up generating a search query based on the persona and the question that we're asking that persona, right? And then we have this retrieval step to search Wikipedia. It's just using the Wikipedia API to fetch some documents, right? And then there's the general web search. The web search is using something called Tavily, which is it's like a search it's like a search API for LLMs, right? So it's um, that's all it is, right? And so we do a few steps of that. Again, when it branches, that's happening in parallel, and then it gets aggregated, right? And so that's what it's doing. So then by the end of this, we end up with um, you know, a whole bunch of, it's 2 steps. We end up with all this information along with links to sources. And so now for every single interview we did, we have all this information, right? All this collection of actual information from the internet, as well as analysis from that persona, like perspective of that persona. And then it goes to this right section, right? So then it just takes all that information from that particular interview and summarizes it into one document, right? And we can see that this ended up outputting um, just this little like mini report here just for this particular person, right? So it's interviewing my tree hugger, and this is what she said based on the sources that were fetched. Um, Looks like they're not fetching many sources. I guess there's not a lot on the internet about pine trees and closure, but this is what it found that's relevant. Then all that stuff gets aggregated together, right? And then we can actually begin the report. We're going to take those 4 different reports and we'll combine them together into one report. And so that gets divided to actually do in parallel to write the report, write the intro, and write the conclusion in parallel. Those are just LM calls. And then all those finished report, all it does, this is just string manipulation. We concatenate those together into a nice looking report. So that's how that works. You guys have any questions on that?
Yeah, how did you come up with this? Like, did you see this somewhere? Like, this is insane to me. Like, you're creating analysts, you're putting that into the system prompt. That's very creative. I would have never thought to use like
Yeah,
this you're doing. That's insane. And in this interview format, I'm actually like my mind has exploded. Like, I'm like how you you put all
yeah,
this
I
together.
know. And when I first saw, so we got this from the line graph guys. This is actually one of their examples. So we replicated it.
I see.
Although ours runs much more in parallel, of course.
That's
Um,
incredibly creative, though. That's crazy.
it's really weird, right? But this is how you use LLMs, right? And actually using a persona, that's a really common technique to get the LM to do what you want, to answer from a particular perspective. And so when I use chatbots, that's something I do, right? Like if I want a chatbot to provide me feedback on a blog post, I say, okay, review this from a perspective of a functional programmer, and then now review it from the perspective of an enterprise Java developer, right? And it really does help a lot in getting useful information out of the LM. And it's the same idea here, right? It's personas used to influence the direction the LM goes. Yeah. This research agent is not particularly good, but it could be made a lot better, right? And I think that's why it's a good example because you're seeing like a very common technique. And what's cool about this is that we can see from the trace like why it's not very good. And actually the retrieval is not very good. If you actually dig into this, well, this is not a good example because the topic is so stupid. But if you had like a real topic, you'd see there's just not that information from the retrieval, right? Like the retrieval can be made a lot better, and that would make the result a lot better as well. But this is a good example because we have some information we can dig in and actually understand why, right? Like why is it doing the things it does, and when it goes off the rails, like you can see maybe you don't know why it went off the rails, but you can actually see the full context of where it went off the rails, and maybe you don't fully understand why the LM decided to do that, but you know what caused it to because you have all the information that it was prompted with. Um, cool. I do think I like this because it is a really good example of defining agents, and you can see here the value of splitting it into nodes.
Yeah.
Um, and yeah, and you could also imagine like testing this, right? Like you may want to test the agent as a whole, and perhaps you have a data set of inputs, and your reference output would be a set of guidelines for what you expect the output to contain, as opposed to like, it's kind of hard to have like a golden truth, like correct. There isn't like a single correct like response for a research report, but you could have a set of guidelines which you could use to evaluate, and then you could easily see here like, oh, I actually would also want to be able to test pieces of this, right? Like if you're just testing as a whole, you don't have enough like uh, it's just like testing any software, right? You need to test the components, right? And so here we want to test, let's just test the analyst portion, right? And actually see, is it doing a job with analysts? Let's actually specifically test the retrieval steps and see that that's doing a good job. And if we had specific focus testing on the retrieval portion, you'd see very quickly it's not doing a good job there. You collect data sets and you'll be able to see that like, oh, it's not producing good results, right? And so that's everything I showed with, well, I'm gonna dive into that more, but the stuff I was showing at the beginning about evaluation, right? Being able to split it like this and then be able to test at this granularity is like super useful for measuring the performance and also ongoing understanding of how it's performing.
So you went a bit fast, but like you showed this little interview thing, right? Was that basically like you had two in one node? Did you have like two LLMs talking to each other? Is
Let's
that what
let's
that was?
actually yeah, let's look at the code. Okay, so this is the research agent. So we have like okay, so this is where it starts, right? So here it's emitting to generate question for every analyst persona, right? And then for generate question, we have like this function, generate question instructions, right? So for persona, right? So it's just a string where it's saying you're an analyst tasked with interviewing experts to learn about a specific topic. Your goal is to boil down to interesting specific insight related to your topic. And then it's right here it's parameterized with the persona and the topic. And so right? It's just a string that we use to prompt the LM, right? And we say chat, and we say, and this is the full. We're giving it here it's getting the full history. We're getting all the messages, which starts empty, right? We're getting all the messages in the conversation so far because this is a loop, as well as this. But now the goal here is to generate a question, right? And so this generates the question, and then here we generate a search query, right? So now based on this full list of messages, let's generate a search query based on the entire interview as well as this new question. What's the search query that we're going to use to, and this is just another LM call. What's the search query we're going to use to get more information, right? So here's the conversation, right? You're given a conversation, which is the stuff that was in the message before. During a well-structured query for traversal related to the conversation, analyze the conversation, pay particular attention to the final question. This causes the LLM to search for information based on the last question, but looking at what we have so far, so it gets something new, something that's different than what it had before. Um, right? And so this node has two LLM calls, right? One to generate a question, one to generate a search query, so we can get information for that question, right? And then you can see it emits a search web, it emits a search Wikipedia. Search web is doing that Tavily call, like I was saying. So that's just that's an API call to do a web search, right? And then search Wikipedia is doing it's actually using Wikipedia's like HTTP API to actually do the search, right? And we get a bunch of documents. And then we're going to emit those documents downstream. So this is all of our fetched documents from the internet, right? And then we ag the research, right? And so this is a vec-ag. This gets everything from Wikipedia and the web search, right? And that's here, right? And then we're going to add that to the conversation, to the context. And then the key part here is, yeah, answer instructions, right? Right. So you're an expert being interviewed by an analyst. So now this is the other side of the interview. Same LM, but other side. So now it's answering from the expert's perspective, right? And so here's the area of focus. Your goal is to answer the question. Here's the context that you got from the search, right? And so it has the full interview, it has the new question, and it has the context, and then some guidelines for how it should answer it, how it should list sources and cite them, and so on. Right? And so it does that. And then you can see down here, if we have passed the turn limit, which defaults to 2, then we're going to go to right section. Otherwise, we loop back to generate question. Does that make sense? Are you able to follow that? High level.
Yeah,
That's Yeah, and maybe before we dive in further, oh, sorry, Kimo is saying something. Apologies.
Yeah, I was just thinking, like when testing this, how do you come up with the prompts and so on? But can the prompts also be like now they are in the program hard coded, but maybe like as input for like in the agent, like maybe have different variations of the prompts and stuff, and for like testing, just was thinking about that, but maybe we get to like other parts of the
Yeah. Yeah. So yeah, you're asking about like the prompts being dynamic for testing.
Yeah, or like
Yeah.
different parameters and like okay, this doesn't work, this works better, and like
Yeah.
that kind of
So
thing. But yeah.
yeah, you could certainly you could parameterize it with you could structure this so that that could be parameterized. Yeah, there's actually something called metadata in Agent-o-rama. Uh, and so metadata is it's basically just information that you provide, and it would just be available to every node. And metadata is also used for telemetry, but you could imagine providing metadata for the prompts for every step, right? And so maybe it'll default to these prompts, but it can be overridden by metadata. And then from here, basically metadata, from here you would say like um, get metadata agent node and say like get, maybe you do it like this, right? Get, right? And maybe you say, answer prompt, and we'll have a default answer prompt.
Okay.
Right? Maybe you do your node like this. So this would be a way to make it completely dynamic, and it would make it so you could actually make that a parameter during testing, right? And it would let you be able to pick and choose which ones you override. That's one way to structure it. Right now, we don't have any like built-in features in Agent-o-rama for like dynamic prompts. That's actually something like Lang, they call that prompt engineering, which it's just version control for prompts where it's managed separately. We may add that to Agent-o-rama, so you'd have a first-class thing, but you can do it with metadata and just make it dynamic in the definition. But yeah, certainly prompts are definitely something you would need to iterate on when trying to make it perform better. Certainly when we were doing Chat-o-rama, which is right, just this chatbot. This lets you ask questions about Agent-o-rama. That's one of the things we iterated on like a ton, was what's the best prompt for the retrieval portion, what's the best prompt for actually asking the LLM to actually provide an answer, and so on.
Yeah, makes sense. Thank you.
Yeah, for sure.
Yeah, maybe it is a good moment to stop for a moment and let your voice rest for a moment, Nathan. We have like 15 minutes to the official time. Some people like to stay longer sometimes, and maybe you wish, Nathan, to think what else you wish to kind of include in this meeting, whether you feel like you missed something that you wish to say, and maybe it is also a good time to see how people are doing, if anybody wishes to ask anything about anything.
Yeah, for sure. Let me see. Well, I did have more to show in terms of like how you actually run this. I guess you guys saw a bit with that. I showed like how you run it. I'm actually yeah. In terms of what I'm running, I'm actually running on in-process cluster right now, and so you can say like start UI as part of creating an in-process cluster, and then you just have the full Agent-o-rama just UI. It works just like a real cluster. So that's what I'm using right here. And I guess the only other stuff I wanted to show was, yeah, I had a little bit about just like, it's super easy to deploy this yourself, like for real, to a real cluster, whether it's a distributed cluster or to a single node cluster. This is it. This is the whole thing to launch this whole thing on a single node cluster. And then I guess I had more to dive into in the particulars of the evaluation portion. There's lots to talk in there, but I guess if you guys want to, we can base it based on what you guys want to dive into, but I have plenty more to show.
So I have a question.
Mm-hmm.
Let's say I wanted to use this today. Would I deploy that free Rama thing, like the 2 nodes that I get, and then put that on top of that, and I can query that cluster in my own web application? Is that? Yep.
That's it. Yeah.
Nice.
So if you're running on AWS, we actually have a public like open source project. It's called Rama AWS Deploy. So this just uses Terraform. So it's a one-click deploy. You can use this to either deploy a distributed cluster or a single node cluster. There's instructions here. But you basically you point it to a Rama release, which you download from our website, and then that'll download Rama, and then from that, it's just one line CLI commands to deploy an Agent-o-rama app. Okay, let me talk a little bit more about evaluation, because this is like a really important topic, and this is something we've learned a lot of lessons from. And maybe more to talk about here. I'm curious also about your guys' experiences evaluating LM applications. But basically, there's three kind of evaluators in Agent-o-rama which you can use for experiments. So a regular evaluator just looks at an individual example run, right? So what was the input and reference output that came from the data set, and then what was the output from actually running that target on that example. Again, the target can be a full agent, or it can just be an individual node of an agent. Right? So for example, here maybe our input is how can I be a better programmer? The reference output is learn Clojure, attend the Clojure conj, and then the LM said learn JavaScript and read computer architecture books. And what an evaluator does is it returns a map of scores, right? Where the key is a score name, and then the value is the score. So in this case, it's saying that's not very helpful, but it's relevant, right? If and depending who you ask, they may disagree with that evaluation. But let's say your evaluator scored it like that. Something else called a summary evaluator, where this is this is stuff that you can't measure looking at they don't make sense on individual examples. They make sense looking at all your examples, right? So this would be an example of entity extraction, extracting entities from an input, and then from this you might produce scores for precision recall, F1 score, false positive rate, like those kinds of like aggregate metrics, which could be very important to know that like as a whole, this is how this target performs for this particular task. Last one's called comparative evaluators. This is a really interesting one. So there are some things where like we look at like these two responses. How can I be a better programmer? Output 1, practice programming every day by building real projects. Output 2, learn languages of new paradigms to expand your mind, embrace immutability and referential transparency. So if you're looking at those individually, well, they're both good advice. They're both good. And so you might score both of them like an 8. Or maybe one's an 8 and one's a 9. But if you look at both of them in comparison, well, the second one's, I think, clearly better. It's much more specific and actionable. And so in comparison, you can clearly see that one's better. So the idea behind comparative evaluators would be, oh, I can run multiple versions of my agent, maybe with different parameters, and actually do a comparative evaluation because maybe it's hard to see which one's better if I do individual evaluations, but I can clearly see which one's better if I do comparative evaluations. So that's the idea behind this. And that's called a comparative experiment, which is a slightly different kind of experiment. When you make evaluators in Agent-o-rama, there's built-in evaluators. These are the ones that are built in. We're probably going to add more later. The one to really highlight here is the LLM judge, where you use an LLM for evaluation. This would be how you configure it, where you give it a prompt. This is the default prompt that you get, but you're probably going to want to customize that depending on the task. Like here it's saying judge the quality of model's output, but you probably want to customize it to something like helpfulness or relevance or like some more specific thing it should be looking at. Now LMs can be really useful for evaluation, but you do have to watch out for like circular logic traps, right? So like it actually makes no sense to like, if you have an LM that produces an output, right, from a prompt, and you just use the same LM to evaluate that output, but it doesn't have any additional information with the evaluation, it makes no sense. It's like asking a student to grade their own test, right? They don't have any other, they filled in the test. What other information do they have to know how good it is? And so if you're using an LM to evaluate an LM, it needs to have it either needs to be looking at a different aspect of it than for the LM that produced the output, or it needs to have other information. So that's what I was saying with like a reference output, right? The reference output can contain guidelines for what it should contain so that, oh, now you actually have something the LM can use to actually evaluate the output of another LM, right? So that's one of the tricky things. But this is really useful because it's automatic evaluation for subjective scores that you could do like, at scale. And you can run this automatically on your production. As I was showing, you can use this for online evaluation to actually see graphs of how it's performing, as well as using it for your experiments. So very important, but also you got to be you got to be careful, and you got to watch what it's doing. Cool. I'll skip the JSON path stuff. And this is just an example of declaring custom evaluators, right? So all this stuff is pluggable, right? So you can, showing in Agent-o-rama, you can declare stores, you can declare agent object, you can also declare evaluator builders, right? And so you're just providing an evaluation function that produces a score. This is like a regex matcher, right? So it's parameterized with the regex, right? And then, you can see it's basically a function of functions, right? The function of parameters, which will be provided in the UI when they build a particular evaluator. In this case, it would have one parameter called regex. And then you'd have the actual function to actually do the evaluation, where here it's just producing a score of just a Boolean match about whether the output matched that regex or not. Cool. This would be what it would look like to do it in the UI to actually build one. Yeah, let's actually just go back to the UI. Yeah, so like, the code here did define regex matcher. So here I'll let's just call it my matcher. Right, we'll give the regex, we're looking for the string happy, let's say. Right, now we have my matcher, right? And let's say we want to actually create a data set, right? So let's create a data set. Right, you can optionally declare a schema for the data set. I'll just skip that for now. Right, this data set, I'll just add some examples manually, right? So input, we'll say, sorry. And reference output we'll say is right, let's make another one that has happy. Right, and then I can go to here, look at experiments, and I can create an experiment on it. Right, we're saying we're going to run on all examples. We're going to target an agent. Yeah, I don't think any of these actually take a single string. So I'm not going to run this because this is actually not going to work, but provide some metadata for the agent. And then, yeah, so this is just saying that we're going to provide you can basically, this is a mapping from how you map the data set input to the actual arguments for the agent, which could be multiple arguments. In this case, we're just going to provide the one argument, which will be the first, which would be the input as a whole. But it could, yeah, if it was like a map, we could do like .a, and that would get like the key A from the map, right? And you can add multiple arguments if you want, but yeah, I'm not going to run this, right? And then you see in my experiment what evaluators I want to use. I've only defined one evaluator, so we say my matcher, and that's it. Then you can say here, like, how many times should it actually run the target against every example? You may want to do more than one just to reduce variance, right? And then how much concurrency do you want? The reason why there's a limit in concurrency is because if you don't limit it, you may overwhelm the OpenAI API, and you'll get throttled, and it'll cause the experiment to fail. So that's why there's a concurrency limit, right? But usually like 4 or something would be fine. And then it'll run parallel across the cluster. You click run. Again, I'm not going to run it because this agent doesn't actually take this as input, but then this would take some time to run across all the examples, depending on how big the data set is, and then you see the experiment results. So super easy. Yeah. Yeah, in terms of experiment results, I guess there's a few interesting things to show here. So like this is the experiment listing. And so here we can see there's 4 experiments here. It just automatically generates these trends charts. So this is just showing like for each evaluator, how is that scoring over time with the experiments you're running. What this means, of course, depends on what your experiments are and whether every experiment tries to be an improvement or if they're just random experiments. But they can be useful to tell you if you're improving or not. And you can see for every experiment there, we have aggregate stats about how it's doing, right? So we can see what was the average latency across example runs, what's the P99 latency, what's the average token count for every run, and then what's the average evaluation for a score for every evaluator that it ran. So in this case, we can see For the most part, they tend to be very grounded, but it's about half of them are correct according to this particular evaluation. Yeah, and again, when you look at experiment results, these just came from when we were doing experiments on chat, but here we had a whole bunch of different evaluators. And so you can see, again, on the left, you can see for this run, how long did it take, what was the token usage, and then on the right, you can see how did it actually score for every individual example, right? So on the experiment listing, you see an aggregate view of how it scored, and in this listing, you can actually see how did it score for every example. And this is all clickable as well. So if you click on view trace on the left, you see the full trace for that run. So running this target on this example. And all the evaluators are also clickable. There's a trace for those as well. So if your evaluators are doing LM calls, you understand how did it even create this evaluation, you'd be able to see it from the trace, which is very, very useful for debugging your evaluators. Cool. Yeah, I mean, there's other features, but any other questions you guys have or stuff you guys want to talk about?
Yeah, so I guess what we've seen in a way is a little bit of your approach nowadays to building a system with Rama, but also it is inspired by those Python graph systems. And in a way, it is quite general, right? Yeah, a lot of this applies to other kinds of async systems with uncertainty. Now I'm kind of curious, would you use that approach again for another situation?
Which approach? You mean like the graph, this kind of graph
Yeah,
approach?
yeah, this graph representation and the traceability and this concept of an experiment, that is kind of
Oh
general.
yeah. Well, I will say that the reason why this works for this use case in particular is because LM calls are so slow. And so the thing, when you have tracing this deep, it does mean that you're doing a durable replicated write in between every single node call. And we're also capturing, like we're actually writing every database call. We're doing writes of every database call that happened and so on. And it's fine in this case because compared to the LM call, like that's nothing. And so we have that we basically the slowness of LLMs gives you the flexibility to do this kind of super detailed tracing and everything that goes along with that. Now for like a regular application, which is like a super high throughput, let's say social network, you can't do that. You can't be recording a trace of for every single call that happens everywhere and writing like doing a replicated write of every single intermediate thing. You just can't do that. So for anything that is inherently slow, this would work great, right? And yeah, I'm glad you noticed that this is a much more general thing than just agents, right? This is orchestration. Orchestration of stuff in parallel defined via this graph mechanism, which is a general thing. But that's my only comment, is it works because of LMs being slow.
Yeah, thank you. Yeah, one example that comes to mind is machine learning engineering, where people
Yeah,
go through, training models and testing them in different scenarios, and
yeah,
often
yeah.
they kind of live system that keeps growing with that. Yeah.
Yeah, and that's another good example of a like that's a very intensive thing that's pretty slow, and that could be another good use for a orchestration tool like this.
Yeah, we're getting close to the official time. Some people may need to leave soon. Maybe you too, Nathan. And does anybody wish to have another brief question before we reach the original, like the official time? Any comments or questions by anybody?
I have a question.
Hey, Ryan.
Um, Hey, my experience so far has been mostly limited to the code agents that are integrated into IDEs or some of the standalone ones like Cloud Code, and then seems like they're inspiring all these or promoting all these different like protocols like MCP and skills and stuff. I was just curious if you had like sort of like a broad take of, this your Agent-o-rama approach compared to some of the mainstream of these other tools, if you've had any experience with those or exposure to those.
Yeah, well, Agent-o-rama is for building agents that you run on behalf of your clients. You wouldn't use Agent-o-rama for people for your users to deploy themselves. So that's very different than using like Cursor or something on your own computer. where the agent's running locally. But in terms of like MCP is actually a good thing. We have a ticket open for that to actually integrate MCP directly in Agent-o-rama. So MCP is just it's basically just like a generalization of tools where it actually fetches the tools dynamically. But yeah, I don't know. Does that answer your question? I'm actually not entirely sure what you were asking.
Yeah, I don't know either. I think so. Yeah, thanks.
Yeah. But yeah, I mean, MCP is the thing about MCP. MCP can backfire because if you're providing too many tools to the agent to the LLM, it can actually confuse the LLM where it doesn't know what to do. And so usually when you're using MCP, you also need a filter to actually limit the number of tools it actually sees, so it doesn't get confused. And so like anyway, we have a ticket over for that to do exactly that, like expose MCP with filtering and all the stuff around that, around caching it and refreshing it as necessary, depending on what the server is doing.
Since Rama, has so many, sort of like expressive potentials on that system level, have you seen any other popular things that for you give like a big kind of red flag code smell where like, okay, this is just not, really clearly, massively thought out or kind of going in the wrong direction? Like,
You mean with like other tools?
yeah, I was just trying to get a sense of your sense of like what you've seen of like other people adopting or industry norms evolving versus your maybe kind of clarified personal vision since you have kind of Rama under your belt,
Yeah. Well, so yeah, I mean, it's still very young, right? There isn't really a norm for this. Certainly not on the JVM. There's a whole bunch of tools out there. Agent-o-rama is unique. Agent-o-rama is the only one that has this amount of like this sophisticated of an evaluation observability system. I think the only other one, I think it's not Spring AI. I think there's one like Spring AI. There's like a fork of Spring AI that has some evaluation capabilities, but I think it doesn't have observability. And like the thing that really like grosses me out about like just about tooling in general, but like, the thing that really is a red flag for me is that when it's like, yeah, you deploy this one system to this piece, and this system to this other piece, and this other system to this other piece, and to actually do this, you end up deploying like 8 different systems, and they often communicate with each other on protocols, and they don't actually know about each other. And so, like that kind of infrastructure sprawl, like um, repulses me. I think it causes a tremendous amount of complexity. There's a tremendous amount of pain. It makes it really also hard to like test things locally. Um, and just I mean, everyone, anyone who's been an engineer for more than a day like knows how painful it is to deal with infrastructure sprawl. And so that is something that is very unique with Rama in that it's able to do the whole stack end to end in one tool. It has deployment built in, it has testing built in, like the whole thing can run locally. Like I didn't show here, but with Agent-o-rama, you can just be running IPC on your cluster while testing against a remote data set that's like on your actual cluster, that's running like on your actual production stuff. And so like that's a big deal. And so like that's like basically the reason why I spent so much time like researching Rama and building it was to eliminate all that complexity that comes from infrastructure sprawl and all these like specialized components that only do one particular issue, and you end up needing so many of them to actually build real applications.
Yeah, I saw you mentioned in your blog some interoperability between Rama modules and Agent-o-rama. In both ways, is it possible to embed Agent-o-rama in a normal cluster running own modules and the other way around too?
Yeah. Rama module, you can, yeah. So I was showing like def agent module. That's just a very thin wrapper around just Rama's def module, but you can add agents to a regular Rama module and you can invoke them from regular Rama as well. And so yeah, it's very easy. I think we have a wiki page on it. Hold on, let me
yeah, so it's documented.
Yeah, let me see. The wiki is pretty, spent a lot of time on the wiki. So yeah, I have a whole page about integrating with regular Rama modules. And so it shows in both Java and Clojure. But yeah, this is, here's like a good example. Oh, I should add a Clojure example here. But sorry, this is Java, but it's very similar in Clojure, right? But Basically, you define a regular Rama module, and then you define an agents topology. And this is the exact same thing as doing def agent module. You create your agents, your stores, and then you just say agent topology def define, and that'll actually add it to the module. So that's how but then you can also have regular Raman module stuff with depots and p-states and topologies and whatnot.
Did you any experiments already with voice streaming inside to Agent-o-rama? I think something like Deep Grammar using audio input on working on in Agent-o-rama.
Audio input. Well, do LMs understand audio input? Can you give? Well, you mean
it's
like
more automatic speech recognition using input as a stream transform into text, so has to be embedded as a separate agent, I think.
Yeah, I mean, it'll just be data, right? It would just be a different form of data, and I guess you'd have to convert it to text before you get to the LM. But I guess you can do that. We haven't tried that ourselves, but I don't see why you couldn't do that.
Okay.
Yeah. Cool. Yeah, and this, by the way, is the repository. It's all open source. It's also a really good example of Rama as well, because it's all basically implemented using Rama's Clojure API. So if you look at like here, a lot of the implementation is here, but this is all just Rama code. This is going to look really foreign to you if you haven't seen this before, but it's doing some pretty cool stuff in here.
Yeah, maybe I'll just say, to people here and people listening to this recording that as usual, we will consider, organizing a study session where we just practice, diving into the code and trying it with a little example and so on. And possibly if we do that, then we will begin with studying Rama a little bit just to get, an understanding of, a cluster, like at least the trivial example of a cluster is and so on. So that's a hope we have on the community side to have those practice sessions soon. And so if anybody listening to this recording has some thoughts about this, then let us chat and maybe plan something together. What do you think, Nathan, about time? We are over time. Do you like to continue if people like to ask more, or do you need to go?
I can stick around for a bit if anyone has any more questions.
Yeah, wonderful. Yeah. Any thoughts, any comments by anybody?
I was just going to say I just watched the Clojure video the other night from the Clojure conference, and then seen your demo. I think even though I don't grok the code exactly yet, but I mean your insistence that it's a simple API and stuff gives me encouragement to go ahead and just try it out.
Yeah, I think you'll find you can learn it very, very quickly.
And I've been using Spectre for many years, and thank you for that. I love that, but I haven't had a chance to really get into Rama yet. But just even that overlap has been encouraging.
Well, if you know Spectre already, that'll help a lot in learning Rama. That's a big part of it. Yeah, I will say in terms of learning in the repository, there's this whole examples directory. So you can just go to the Clojure examples and you can just run it. So that's actually how I'm running it here. So let me actually just turn it off. But you can literally just clone it, just make a REPL, just pick an agent. So you can run the research agent. Like if you'd want just the research agent, you could just require this namespace. Right, and then it just has a run agent at the bottom, which sets up in-process cluster, it starts the UI and launches it. So we can actually do it. It'll take a minute to load all the dependencies. But yeah, it's just you can just it'll take it takes 2 minutes to do this, to clone it and run this. All right, and so now you just go to 1974. just launching the module right now. That'll take a minute, and then it'll be the exact same thing I was showing in the presentation. Cool, it ran. Yeah, so that's it. That's all it takes to try this out. This actually runs it also has like a little CLI driver to do one invocation of it, which is basically the same code I was showing before, but you could also just invoke it from here, like I was showing during the presentation.
Okay, and that was just one of the agent files?
Yeah, I just did research agent under examples of scicloj. It's in agent. And then there's a whole bunch of examples in here. Sorry, this is actually not, let me go to master. Okay, there's much fewer in here, right? Probably research agent probably not, this is a bit more complicated, right? Probably don't want to start with that, but React agent's pretty good because this is like the most basic agent of just like that loop of doing a prompt with some tool calls. We also have some basic agents here, which are doing like very little. But like here's human input agent, which is doing like one little bit of human input with a model call. You can look at what's the simplest one here? I think there's one called basic agent. Yeah, basic agent is just doing like, it's essentially like hello world. So just one node and producing a result. And just, things just doing different patterns. So this one has a few nodes, which are routing between nodes depending on the text of the input. So this is a good way, and you can just run all of these and then play with the code and learn it, right? There's not that much to learn. Has anyone here actually built like an actual LM application?
I'm kind of in the middle of doing that right now, right? So like when Opus 4.5 dropped, I'm able to kind of just produce a lot of stuff, with that. I spent probably like 95% of my time just coding manually before Opus 4.5, and then like having LLMs do like specific tasks. But with Opus 4.5, I can pretty much stay out of Emacs like for everything. Especially like I said before, open code kind of giving me the observability of how an LLM actually kind of works and what it's doing versus using Cloud Code for a while. You just get like the smallest little thing and you get no feedback. So that's kind of taught me a lot, right? So that's kind of in doing all this stuff, I'm kind of getting into this a bit more now. So what I did realize though is that your question, and it seems like most people, this is new to a lot of people, right? Like everyone I work with, it's like a black box mystery still, right? Like people who use Cursor and Windsurf, they have no idea how context windows work. They don't know what's being like thrown into the, what the LLM knows. They don't know, like, it's just kind of a magic thing, right? So I feel like what you're making this tool is kind of like way ahead of like where most people are in terms of even what they can imagine they can build.
Well, yeah, possibly.
Yeah.
Yeah.
Yeah. It is interesting to think about this graph representation situation where you represent a software system as a graph, but the graph is also generated by a software system. So you have this meta situation, right? Where we're not representing the whole thing because the graph emerges after you do something. So it is data dependent, right? So there is actually a UI problem, right? In letting the user see the whole flow is a graph, right?
You mean just the difference between like the trace versus the actual definition?
Yeah. I mean, and I think that it is common also in other graph situations that, a graph is generated and you wish to have a complete story in this graph DAG way, but you cannot actually, I mean, not the usual way because it is dynamic.
It depends. If your graph has 100,000 nodes in it, then it's going to be harder to navigate. But agent trace graphs tend to be, under 100 nodes. So that's something that a human can go through and analyze.
Do you ever think about like building a graph UI tool where people, could sort of draw the arrows and edges and sort of informally define or somewhat less formally define an agent flow that way?
Yeah, I don't know. That's like the no code builder kind of thing. Could certainly do
Yes.
that, but at the end of the day, you still need to express logic. So that would be limited if you're not able to actually just code. Or maybe you have a hybrid where you can express the graph visually, but then you could insert like code. But at that point, why not just do the whole thing as code?
During your presentation, I asked myself, what is the difference between a node and a sub-agent? When to use one or the other? What is your guideline to export behavior to a sub-agent? Is this generally because of it is running independently, or?
Yeah, you could do it. It could just be maybe common behavior. Maybe it's just easier to structure it that way. It's just maybe it's common behavior that maybe it's like common complex behavior with a whole bunch of like aggregation in it that you want to use from multiple places within the overall agent. And maybe in that case, it's easier to specify as just its own little sub-agent graph. Or maybe it'd be because you're at a bigger company and that different teams are responsible for it's more like a microservice in that case, right?
Okay.
Different teams are responsible for that and you want to use it. Certainly the agents that we've been building, we've just done them as single agents. But it's easy to imagine a whole bunch of reasons why you might need sub-agents.
And sub-agent could be deployed in an agent in a separate module and joined together in okay.
Yeah, you can use agents from other modules as well as you can use stores from other modules as well.
Okay.
Yeah, I didn't show it in the presentation, but agents can also be recursive and mutually recursive. I haven't found I haven't found a case where I needed that yet, but it's just a natural thing that flows from the API. When you're able to get an agent client inside the node and call it, then it's just able to be recursive, which is pretty cool. And that's actually a difference. That's one of the differences from LangGraph, where LangGraph has its own sub-agent concept, kind of, but it's unable to be recursive, which just like hints at how it's not as like first class as this is what we have here.
Yeah, I suggest that in a moment I will stop recording just because some people like to chat unrecorded afterwards. And maybe Nathan, you wish to kind of conclude the recorded part with, anything you wish to say more before we end.
Well, I don't think I think I said everything I think that needs to be said. Yeah, I don't have anything else.
Yeah, thanks. Yeah, so thanks so much. It was lovely to learn from you, and thank you thank you to our listeners as always, to everybody who was here. See you on the next times.